So thank you very much. Today I'm going to continue the exposition on partial regularity for minimizers of functionals and solutions to elliptic systems that I started yesterday. So in the variational setting, let me recall you what is the situation. So the situation is the following. You take a minimizer, a local minimizer of a variational integrand, depending on all these variables. The variational integral and the integrand actually is supposed to have p growth. For simplicity, I'm going to consider the case p larger or equal than 2, but everything I'm going to tell you is actually already non-trivial in the p equals to 2 case. And the second derivatives and the eigenvalues of the second derivatives, which are this one, this is a bound of for the highest eigenvalue. This is a lower bound for the eigenvalue. So in particular, the ratio is L over nu, and the operator is uniformly elliptic. And the point I would like to stress is that the dependence on the coefficients is at rate alpha. So under these conditions, no Euler-Lagrange equation of the functional can be written, because this would assume that you can differentiate with respect to the u variable, but this is actually not the case. This is actually not the case. So prototype. And let me also tell you that even if such a Euler-Lagrange could be written, then you would end up with a system with so-called critical growth, because the Euler-Lagrange equation of the functional would look like this is the gradient variable, like this, and would have a right-hand side involving the differentiation with the with respect to the u variable, and this would actually be controlled by something which is critical growth. So it is very difficult to deal with systems with critical growth unless you do not have a smallness condition on the right-hand side, which is not the case in general here. So nevertheless, the partial regularity theory tells you that you can use just minimality to prove that to prove partial regularity statements. This, for instance, occurs in harmonic maps. For instance, in harmonic maps or in several of these problems whose Euler-Lagrange equation has critical growth. Also, for instance, this is the case of quasi-convex functionals. Then if you just use that a function is a critical point, that it solves the Euler-Lagrange equation, you may come up with very little, with nothing actually. But if you add and use directly the minimality properties, then you can show that minimizers are let's say regular, and solutions are and that's the like. So the main statement is the following one. So U is C1 alpha half. This can be proved outside a singular set, which is a closed subset with a zero measure, and this can be included in two sets. So the sets of no Lebesgue points of the gradient. So where this is not bounded and this is not going to 0. And the other part, which is let's say the smaller one, is the same thing, lim x such that rho of x, then you can rho x, u minus u, p rho x, py, p is larger than 0, or the lim of the averages, and this is the average, is going to plus infinity. This is the ball centered at x. This is the ball centered at x. And this is y. So x such that. Now, the problem I would like to discuss is the following one. Now we know that the singular set has zero measure. And this was actually the status of the theory until the beginning of the 80s, let's say 81, 82. And then the open problem was that, and of course the same thing can be held to prove for systems. I'll go for systems of this type. Where you have similar assumptions. Similar assumptions is that a of a, x of u, z controls ellipticity with rate for every z, couple of gradients, and of course its derivatives are bounded by 1 plus z p minus 2 over 2. And you have that's the same thing, of course. If you believe that A can be written in the variational case as this, okay, this is what you get. And finally, you have Hilder continuity assumptions, which are similar to the ones stated before. That is, this is the modulus of continuity with respect to the coefficients 1 plus z squared p minus 1 over 2. So in this case, you can end up with the same partial regularity statement. That is, u belongs to C1 alpha. You actually gain from alpha half to half. You get the gain, the usual thing from omega. And this is 0. So these are the two statements. For this, you can argue using directly going to the system. Of course, you have to start always with W1P energy solution. Okay? And this is the thing. Okay, so now the open problem the problem is the next problem. Is not to understand if the singular set can be estimated. So if the dimension of the singular set is less than n, and if the dimension of the singular set is less than n, and if there are explicit bounds for the house of dimension. So you want to prove that the singular set is small beyond being negligible. So where, of course, this is the ambient dimension. So you want to go from n to lower than n. So a rather satisfying solution to this problem occurred for systems in two papers of mine, 0304. I think one is on ARM and one is on Calc-var, and for systems. And for functionals, which is the most delicate case, is by Christensen and myself in a paper on ARMA 06. So in the answer, so you can see it took something like 25 years to fix this. Actually, I think there have been several heavy attempts for this, and several attempts for this. Several attempts for this, and now let me show you what is the idea. And in particular, then there was also another problem which was even more delicate. That is the following one. Assume that you couple, for instance, consider the system in a bounded domain, which is now regular. Let's say that the domain is smooth, but actually C1 alpha is sufficient. And assume that you also have a boundary condition which is regular. So you have criteria for regular points, but the issue was that even not the existence of one regular point. So you see, you have such a system, for instance, A of x of du. Let me consider the usual, the simplest case, where there is no dependence on u. So you solve the boundary problem. This can be solved by means of monotonicity methods. And then you want to know, so if this is an equation, and if this is the boundary value, the boundary values are regular, then you know that the solution is C1 alpha up to the boundary. This is classical. If you want to know what happens in the case of general systems, then you see one problem. What is the regular set? the regular set is negligible. And now the point is that the whole boundary is Hausdorff dimension n minus 1. So the whole boundary is by definition negligible. So a priori, the current criteria do not guarantee even the existence of one regular boundary point. And this was eventually fixed for systems of this type, as I'm going to tell you later in two papers. One is by Dudza, Christensen, and myself, 07, and for systems, and another one is by Christensen and myself, 10 maybe, for systems and functionals, once again, proving that almost every boundary point with respect to the surface measure is regular under suitable assumption. So this is the, let's say, the largest bootstrap, because you pass from a situation where even the existence of one boundary regular point is not known, and in fact there are counterexamples on which you have a very regular vector field A, a smooth boundary datum, a smooth boundary, nevertheless singularities occur at the boundary because of the vectorial situation. So the vectorial case carries along singularities in a natural way just because you are in the vectorial setting. So smooth boundary datum, smooth boundary, smooth vector fields, nevertheless singularities occur up to the boundary. So even the fact that you are prescribing that the solution is actually getting its boundary value is sufficient to force regularity up to the boundary. So singularities occur nevertheless. So even the existence of one regular boundary point was unknown, because essentially you carry over this characterization up to the boundary, but while this characterization yields almost everywhere regularity in the interior, because almost every point is a Lebesgue point, and actually these sets are closed, this can be shown to be closed. So the new point is that these irregularities are closed. When you carry over up to the boundary, this characterization, you come up with nothing, because the full boundary, the whole boundary is definitely zero measure. So these are this is a set of solutions that we have. Okay, to understand what are the results, let me tell you let me show you the following thing, that you end up what it was known, and essentially the point was the presence of the coefficient, the lower the coefficients that do not allow you to handle with the situation. You can, for instance, these open problems are stated in a well-known book by Giaquinta. There are two books by Giaquinta, one from Princeton, 81, and one from Zurich, 88, 93, and they are explicitly stated. These open problems are explicitly stated there, because it's essentially, after you prove partial regularity, then you wonder what do you want to do. Okay, let me now go to a classical way of estimating the Hausdorff measure, that the Hausdorff measure of the singular set, that actually goes back to a method that goes back to Giusti and Federer, as far as I know. This is commonly regarded to be Giusti and Federer. Okay. Okay, the lemma is the following one. Lemma. You do consider a measure, a radon measure, with locally finite mass in Rn. So we are in Rn. And you do consider the set where or in a bounded open subset of Rn, let's say a bounded open subset, it is sufficient. I mean, in all Rn, because you want to, this is a local fact, such that the limit, when you take the ball over B rho to the sigma, when rho goes to 0, it's larger than 0. So you are measuring so it's a positive measure, positive measure. Positive measure. Otherwise, you switch to the bounded variation of the measure, and there's no problem. So you want to know where the measure concentrates more than this. And of course, if you want to be, if sigma is larger, right, then this is getting, it's an easier condition. So then the house of measure of this set is less than or equal than sigma. What is the main point? What is the main point is the fact that this is really a measure and it's a super additive quantity. So if you look at this is based on Vitali's covering, you go to the proof. And this is very, very, very useful. Okay, now let me show you briefly how this can be used to estimate the house of dimension of the singular set of a functional like this. Or of a systems like this. And from now on, I will always take p equals to 2 for simplicity. Okay, then the same thing can be carried over for the case p different than 2. Okay, now what is the difference between this functional and the previous one? Now you have the Euler-Lagrange equation of the functional, and the Euler-Lagrange equation looks exactly as this system, where A is the gradient of f. Okay. In a distributional fashion, this looks like equal to 0 for every phi in omega. Now you do the usual thing. You take as a test function the derivative of something else, right? You differentiate. You apply difference quotient methods, and since p is equal to 2, then you come up with the fact that the gradient itself is in W12 locally. So the gradient is differentiable. Okay? How do you do this? You put this guy here. You integrate by parts. So this is ds phi. So now you switch. You take the second derivatives of phi. And this is d ds of u d phi. And now you will choose something like phi eta of the gradient of u. And then you'll come up with the local estimate. So in order to do this, you have to be able to switch this on the left-hand side, and therefore this quantity must be differentiable. So you use the differentiability twice. First to get the Euler-Lagrange equation, and then to differentiate the Euler-Lagrange equation, that is, you pass to the so-called second variation equation. So anyway, you end up with the following thing. But now, obvious remark, you want to bound this quantity. You want to bound this quantity, and you can do it using Poincaré's inequality. You can do it Poincaré's inequality, and this is less than or equal, and c rho squared the second derivatives of u, because you have second derivatives at your disposal. And so this is, of course, less than or equal than rho 2 minus n d rho dx. And now you make the trivial observation that this is a measure, this is a positive measure, and therefore you can estimate the size where this is larger than 0, where the limit is larger than 0, which is the singular set of the first functional, of which is essentially the singular set is estimated by the set where this is larger than 0, right? And so you immediately end up with the fact that the so-called U1, which is under these conditions, the whole singular set, then the house of dimension is less than n minus 2, because you apply that lemma with sigma over 2. And that's the end of the story. So this is a classical fact using this Giuseppe thing. Now, if you take a simple system of this type under the previous assumption where this is alpha Hilbert continuous, you cannot carry over the following thing because you have a solution, so you have a system of this type, but when you switch from S to the S, you cannot now differentiate this object because only Hilbert continuity is allowed. So you cannot get with the second derivatives of the functional. So the point is now the following one. You want to carry over the same argument but using so-called fractional Sobolev spaces. Fractional Sobolev, so see, this has been done in O3 or O4 and actually in O2. This is now, these fractional Sobolev spaces are very, very popular, even too much popular probably. And but at that time they were not very much used. So what are fractional Sobolev spaces? You declare, okay, there are infinitely many ways actually to declare that a function is to express the concept that a functional is fractionally differentiable. But one way uses the so-called Gallardon's norm. And you see that you say that this is in WS gamma for S in 0, 1. So S is not allowed to be 1 here. Gamma is larger than 1 if and only if U belongs itself to L gamma. And the following quantity, which is called Gallardo semi-norm, turns out to be finite so dimensionally speaking, n cancels one integral. So this tells you that the oscillations of U measured in the L gamma norm should be small enough to compensate the blow-up of this kernel. So in a certain sense, this is a Hilbert continuity at rate S, but measured not in the L infinity norm, but in the L gamma norm. So these object scales should be intended as something like this. But of course, this is just fantasy. So it's a bad thought. Okay, so we call this guy the Gallardo semi-norm, and we make the following observation. We make the following observation that if you examine carefully the difference quotient method, you can prove that the gradient is in W12 under these conditions. But in this case, the gradient turns out to be in W sigma 2 for every sigma less than alpha. So it's almost in W alpha 2. Oh, okay, S for every S less than alpha. So the Hilbert continuity is now read in terms of differentiability of the gradient. The next step you do is the following thing. You observe that fractional Sobolev spaces feature their own Poincaré type inequalities. So what is Poincaré type inequalities? It's something that allows you to estimate the oscillations with the derivative, so you plug this out and you get a difference quotient, something which is dimensionally a difference quotient. Now, the rate of differentiability here is not full, but it's almost alpha. And therefore, you can do the following fractional Poincaré inequalities. This holds for this. I will state it for the gradient, while it holds for any fractional function. The proof of this is extremely simple. It's 2 lines. So you can bound this guy. Okay. You get this guy. So what would you get here with a full derivative? You would get rho 2. What would you get with an S derivative? You would get rho 2s. So it's rho 2s ux minus dy to x minus y n plus 2s dx dy is 0, 0. So let's check for the homogeneity. Here you have a gradient, here you have a gradient. N cancels with an integral, 2s cancels with 2s, so it's perfect. Now, the next observation is that if you look at the proof of this lemma, you see that you don't need that this is a random measure, but this is something which is, well defined on all Borel sets, and just satisfies the following superadditivity conditions. So if you take a sequence of these joint subsets, let's say AK, then the sum over K of this AK is less than or equal than the union of AK. So this is, measures, they are subadditive, so they reverse this. Equality holds when all these are disjoints, while here you get that this is superadditive. And this makes you this work. Now, the point is that if you define the following quantity, A, this quantity is superadditive. It's not difficult to understand because, you see, this is a double integral. So when you plug in the sum of these guys, you just get the diagonal. While if you plug in the full object here, you get the full space. Now, you apply the lemma with mu, which is this quantity, thanks to this Poincaré. And what you get is that the house of measure of the singular set, is less than or equal than n minus 2s for every s less than alpha. And therefore, by upper semi-continuity of the dimension, it's alpha. So that's the result of this paper, So it's a simple observation. It's not very difficult, but the observation is that you can commute the Hilbert continuity into a fractional differentiability and then apply this argument. There are plenty of ways to prove this. This is just a simple way, but then you can go to potential theory and blah, blah. The only thing is that this actually holds for solutions to systems. This was surprisingly not observed, that you could do this difference quotient argument in this setting and do this. Of course, this is just a toy model, because I did consider the situation the simplest situation, where you have a system of this type. So the house of dimension is n minus 2 half. But of course, you immediately understand that now the rate of discontinuity of continuity with respect to the x variable reflects on the house of dimension. So this is a sort of Schauder estimate for the singular set, for the dimension of the singular set. And it's not difficult to understand how it works, because the more you tend to be discontinuous with respect to the external ingredient, that is x, the more you tend to form singularities, the more you are allowed to do that. In fact, when there is this measurable, you can even not get partial regularity. There are nice counterexamples of Yon, Mali, and Starad. This is the Prague School of Nature, so the 670s, where they get a simple linear system with measurable coefficients, and you can prove that even partial regularity fails. So the singular set, the set of singularities is dense. Singularities are dense. So there is no open subset, no little open subset where you can get regularity. So essentially, they take the counterexample, the original counterexample of Daejeon, and then they distribute the singularity, the one-point singularity imagined by Daejeon, a dense set of rational points, and then they distribute singularities everywhere. So this tells you that this is in accordance to this, because when you lose, when alpha goes to 0, you see that everything tends to disappear. Now you immediately see that you can, if you try to carry over this method to systems of this type, then there is a problem. Why? Because this is Hilbert continuous with respect to x. But then if you think that this is an additional coefficient, this a priori is just measurable. So this method doesn't carry over directly to this situation. The situation is even worse when you get functionals like this. Why? Because here, not only you have a measurable dependence, but you cannot even write the Euler-Lagrange equation. You cannot even write the Euler-Lagrange equation. So, because essentially the dependence on with this variable of the integrand is just Hilbert. So no differentiability is allowed. So, in order to overcome these difficulties, then my observation was that it is true that if you display this as an additional measurable dependence on x, you lose everything. But this is not any additional measurable dependence. This is a special measurable dependence because this depends on the solution itself. So you have to be able to bootstrap in a way something global, because you cannot restrict yourself on the singular set. The singular set is the object you want to estimate. So you have to forget partial regularity, and you have to have an additional global regularity information. So you want to use the fact that this additional potentially measurable dependence appears through the occurrence of u, which is the solution itself. So you look back and you wonder, what is the only regularity information you have on the solution other than partial regularity? The only regularity information you have on the solution is, at this stage, higher integrability. So the higher integrability that occurs also with full measurable dependence on the functional tells you that you start, in this case we are restricting with the W12 solution, and then this bootstrap into something which is Q, and Q is larger than 2. That's Gering's lemma. And so in this second paper, what I did was to use this in the framework of the previous method, and to use this in order to get that although you have an a priori measurable dependence, you can still prove that U belongs to WS2 for every S less than the minimum between 2 alpha and Q minus 2. And this is, so what I did was to, actually this occurred with two papers. The first one of myself, where this is with some exponent, and then with this exponent, it's in a later paper of Christensen, but the technique is the same. So in this paper, I gave the complete solution to the problem for systems, proving the following fact. So in other words, this is a fractional counterpart of Gering's lemma. You turn higher integrability into higher differentiability. If you think better, this is perfectly in the nature of the problem, because all these problems are ruled by Caccioppoli type inequalities, where you control higher order objects with lower order objects. So therefore, a regularity information on one object should improve into a higher regularity information. Yes? No. Oh, sorry. Yeah, U is. Thank you very much. I actually was intending to say that this belongs to L2. This is very important, thanks, because otherwise this would have been completely trivial. LQ, right, the gradient. I just forgot about, I should have written this. So let me repeat. You start from an L2 solution, and then Gering's lemma gets you an LQ solution. Now the next step is to transform this higher integrability into a higher fractional differentiability. As a result, then you know that the dimension of the singular set is less than or equal than this quantity. And this is for systems. This is for systems. So this allows you to do the following thing. And when you go to functionals, you have to overcome an additional difficulty. And this was done in this paper with Jan Christensen. And there, we were able to prove directly that du is in WS2 for every S less than the minimum between this time alpha rather than 2 alpha and Q minus 2. So it's a very quantitative information. Actually, there's a loss between from 2 alpha exactly as you get a loss for in partial regularity. But still, this quantity is positive. And once again, the issue is that you commute higher integrability into higher differentiability. And so this gives the full solution to this problem. Actually, the Hausdorff dimension of the singular set is always less than n. So this is the, let's say, the final step in this partial regularity program started by Morey, Giusti Miranda, Jacquinta, Evans, Michel Diffuscon, blah, blah. So it took 25 years more or less, but at least at the end it's done. And of course, now you might wonder if you can make some improvements of this estimate. And there are improvements. Because you see, you pass from n minus 2 alpha to this quantity, or to this quantity, and the worsening, of course, given by the following object. Okay, how do you... and so the point is that the appearance of U carries over an additional a priori measurable dependence that you should compensate with a higher integrability. So you wonder, when U is not affecting directly the higher order, let's say the regularizing term, what happens then? And then, for instance, there's another theorem by Christensen and myself that tells you the following. Assume that you have this functional, which is actually the functional originally considered by Jacquinta and Giusti. Where there's a splitting structure. So you separate W from the gradient. So this satisfies the usual conditions as above. Well, this is just bounded function, which is Hilbert continuous with respect to the alpha variable and even measurable with respect to x. So you get even measurability of here, right? And then you can prove that under these conditions, then dimension of the singular set is less than or equal than n minus alpha always. So this is the effect of decoupling the bad object from the regularizing term. You immediately see why you can even allow measurability, because essentially it is true that you get alpha Hilbert continuity, but looks a priori measurable in W. It is in some sense the counterpart of this result. This is n minus 2 alpha, and this is minus alpha. Observe that this is once again a non-differentiable functional. It's non-differentiable because the Euler-Lagrange equation. This is cannot be written because there is no differentiability with respect to this argument of the integrand. This is originally the the example considered by Jaguint and Juste in their famous paper from 91, from Evert and Jaguint and Juste in their famous papers. And of course, let me conclude this part with two remarks. And the first remark is the following thing. It is well known that in 2 dimensions, of course, everything here is okay for every p larger or equal than 2, and also for p less than 2 up to a certain extent, where you should just replace this with this, and with this, and you start with this, and you will get something like this. Okay, and here will be every alpha with a different alpha. Okay, actually, there are other cases where you can get this estimate. Let me just give you one theorem that tells you the following. Consider once again this complete functional for p larger or equal than 2. And now, with p growth, and now assume that you are in some sense in low dimensions. It can be proved that the singular set doesn't occur in dimension 2, always. So the singular set is empty. It's not very difficult. This is a typical 2-dimensional effect, because 2-dimensional systems look very much as equations. Actually, you can slightly improve this, and actually considerably improve when p is larger than 2. And in fact, when n is less than or equal than p plus 2, you can always go back to this estimate. So this estimate works either you have a splitting structure, or the dimension is not very large. In particular, for p is equal to 2, this holds up to dimension 4. And so this is again in the paper with Christensen. And actually, the same result holds for systems of this type. And then the Hausdorff dimension of the singular set is less than or equal than n minus 2 alpha. This time you always improve from alpha to 2 alpha when you pass from minimizers to solutions to general systems. So we have that all in all, this dimension, this Hausdorff dimension holds for systems when you have these structure conditions. This is holds for n less than p plus 2, and this is always. So why this remark is important? Because now you go back, because with this result at your disposal, you can finally give an answer to the last open problem of the theory, that is the existence of regular boundary points. As I told you, at that time, even the existence of one regular boundary point was not known. And now, under suitable assumptions, we can find a large class of systems for which almost every boundary point with respect to the surface measure is a regular point. So which was the problem for partial regularity is that the dimension of the boundary is n minus 1, and this is always negligible. But now you can find regular points if this dimension is larger than the singular set of the dimension. So if you can prove, when you do consider problems of this type, Dirichlet problems of this type on the boundary, U of course is smooth, you don't care, the boundary is smooth. Actually, you can get less than smoothness, but the point is not this one. So if you assume that the boundary dimension is larger than the estimation, then you'll get that almost every boundary point is regular. This holds if this is less than larger than 1/2, and therefore, for alpha larger than 1/2, you get that almost every boundary point is regular. So you switch from a situation where even the existence of one regular boundary point was not clear to the fact that almost every boundary point with respect to the proper measure, that's the n-1 Hausdorff dimension measure concentrated up the boundary, is regular. So this holds for this system, and this is in this paper with Dutzer and Christensen. And so this is also a problem that remained open for more than 25 years. And of course, when n is less than p plus 2, then you can prove this also for the Dirichlet problem of the complete system. I would also like to point out that the method is now the boundarization of this method. You prove that these fractional estimates occur up to the boundary. Then you prove the lemma, and then you finally impose the condition that the Hausdorff dimension, that the estimation is less than the ambient dimension, which is now n-1. Because the singular set should be smaller than the dimension of the boundary in order to prove the existence of boundary regular points. Okay? And finally, in a later paper, we did the same thing for minimizers of functionals of this type. And the only result known at the time was in a paper by Jost and Meyer, that we're able to prove this only with quadratic integrals. So the only result was from Jost and Meyer from 83. They proved that almost every boundary point is regular, but you have to have the structure of a quadratic integrand. And so the improvement from this very special structure to this general structure is now very huge. And this is the last of, let's say, 5 papers I dedicated to the subject that essentially give a complete picture, and then they are able to fix these two problems, the estimation of the singular set and the problems of existence of boundary regular points. Of course, the case for special structures allowing for the singular set to be empty is a very actual problem. Essentially, there are special structures under which the singular set is known to be empty, and the most famous one is the quasi-diagonal structure. So you have a function here, and you have a system done in this way. So the most special one is the P-Laplacian structure, where you have this. So it's a quasi-diagonal structure. And this is a very famous paper by Uhlenbeck from 77. But out of that, there is very little. I mean, there are special structures, and there are recent interesting papers by Bulicek and Fraze, where they address other structures, and these are interesting. Okay, so that concludes another part of this series of lectures, and now I will, and this in particular concludes the part that I would like to dedicate to vectorial problems. Now we go to a different topic, and we go to non-uniformly elliptic problems. Okay, what about non-uniform ellipticity? So from now on, let me specify, okay, the topic of non-uniformly elliptic problem is a very classical problem, is a very classical one in PDEs, and goes back to the end of the 60s, because, for instance, the minimal surface equation is a classical example of a non-uniformly elliptic problem, and non-uniformly elliptic problems have been analyzed at length by a series of distinguished authors, like, for instance, Giuseppe Mingione, Georgi, first of all, and also Simon, Daejeon, Uraltseva, many others, Lieberman, and especially in the context of the calculus of variations by Marcellini. Okay, the thing is the following. We are now analyzing variational integrants of this type. Variational integrants of this type. And okay, what are the assumptions we were considering before, at least those with respect to the gradient variables that determine ellipticity? We have growth assumptions, like z to the p plus 1, z to the p. And we had to prescribe also the growth with respect to the lowest and the highest eigenvalues, which are the following one. And I'll tell you something later. This is suitably smooth. And let me specify one thing that now I'm going to consider: minimizers and competitors, which are scalar valued, scalar case. So I go back to the scalar case. So I'll not touch, in this respect, the vectorial one. Okay, but now there are functionals that are definitely not falling into this category. For instance, if you get this functional, log e plus 1 plus w, this doesn't satisfy that. So this is let's say, a small perturbation of a polynomial growth functional. Then there are so-called anisotropic ones, which are the following one. For instance, take just the last derivative. And more in general, functions that are elliptic, but where you replace, and this is an Horowitz function. Okay, so these functionals do not satisfy this, but they are seen to satisfy the following growth assumptions when you replace this by q, this by q, this by q for some q larger than p. So these are called PQ growth functionals. These are called PQ growth functionals, and the theory has been studied at length in a series of papers by Marcellini and many other authors, also by Lieberman and blah, blah. So what is the standard feature of those functionals? Well, the standard feature, oh, no, this is not P, sorry. This is not QSP. So what is the standard feature? The standard feature is that the rate of regularization of an elliptic equation can be measured by the ratio between the highest and the lowest eigenvalue. Okay, now if you look at the second variation of the functional, what is the rate of ellipticity of this functional? The largest eigenvalue can be bounded by this guy, while the lowest one can be lower bounded by this guy. And when you plug in the gradient, you'll get this gradient of a minimizer in the Euler-Lagrange equation. Because the Euler-Lagrange equation of this functional is, of course, equal to 0. And from now on, I will always refer to the partial symbol as a derivative with respect to the gradient variable. So when the gradient is large, this grows like q minus p. So you see, the focal point of the theory usually is to prove that the gradient is bounded, and then you can prove that the solution is more regular. Now you see an abstraction. Why? Because on one end, what you want to exclude is the fact that the gradient becomes unbounded. So the gradient could become unbounded. But if the gradient becomes unbounded, you lose control on the ratio between the highest and the lowest eigenvalue. So this is the obstruction. And so the nice thing is that you can still prove regularity theorems, providing conditions between the Q and P and the dimension n, allowing you to say that this difference is not blowing up too fast. It's not too large. So there's a theorem by Marcelli for functionals that are depending just on the gradient. Under these assumptions, then Marcelli proves that if Q over P is less than 1 plus 2 over n, then U is in L infinity log. Once you know that the gradient is in L infinity log, then this ratio is bounded when you consider it on the Euler-Lagrange equation, and therefore you can apply the usual techniques. So the focal point of the theory is to prove that the gradient is bounded, that is something that turns back your functional to the realm of uniformly elliptic ones. And there's a large theory of this. And of course, there are hidden interpolation effects because this is based on a suitable variations of Moses iteration. That allows you to express the catch between Q and P and the dimension n. If you, for instance, assume that the solution is a bit better, assuming a priori that the solution is a bit better gives that the solution should grow less, and therefore should give an improvement. And for instance, there are papers by Ujaltsev and Urdaletova by Choe and by Esposito, Leonetti, and myself, where it can be proved that, for instance, if you assume that U is bounded, and this is information that, for instance, might come from a boundary value, because maximum principles still hold for such functionals, and therefore, if the boundary datum is bounded, then the solution is bounded, it's itself bounded. And then if Q is less than P plus 2, then you get, once again, an infinity. Roughly speaking, you know that what is the threshold for Sobolev embedding to determine that the solution is bounded or not is the fact that the solution is in Ln or is not, right? And when the solution is bounded means that the threshold determined by n becomes unreal, because it becomes immaterial, and therefore n doesn't occur anymore. Is the philosophical explanation. Now, what I would like to now, let me tell you that PQ growth conditions do not catch all the possible functionals. And for instance, there are functionals like this, for which still you can prove that minimizers are regular, but I will not touch this. Today I'd like to mention some recent results and new phenomenon for classes of functionals that do not fall into this realm. Let's say actually they do fall into this realm, but I would like to examine a new phenomenon that occurs only for these functionals, that is the dependence on x. So you see, this theorem holds when there is no dependence on x. Now I really would like to understand what happens when the presence of x is present, and let me consider two functionals actually introduced by Zhikov. The first is very famous, and it's the easiest one, the variable exponent functional. And the second is the hard one, which is a double phase functional. And the point here is that here Px is allowed to be between 1 and plus infinity. But in the second one, A of x is larger than 0. Larger or equal than 0. So you see, in both cases, the real nature of the PQ of the non-uniform ellipticity is given by the fact that when x varies, the growth with respect to the gradient varies. And so this tells you that there's a subtle interaction between the variability of your coefficient and the ellipticity. Now you know that when q is equal to p, passing from these functionals to such functionals, it's a matter of perturbation. And that's Schauder theory, right? So you freeze at one point, you make comparisons, and blah, blah. And now you immediately see that this cannot be the case for such functionals. And this cannot be the case because the real nature of the functional, that is the ellipticity with respect to the gradient variable, is determined by x. So if you change x, the rate of ellipticity changes. And this is particularly easily displayable in the second case, because when a, at those points when a is larger than 0, this functional exhibits q growth. But when a goes to 0, then you have p growth. So you have a double phase, a p phase, and a q phase. And in fact, there's a surprising phenomenon, firstly pointed out in a paper by Esposito, Leonetti, and myself. Dates back a long ago. 04 actually was written in submitted in 01. It took a long time to be analyzed. And where we provide the following example. We take a coefficient which is larger or equal than 0. This belongs to C0 alpha, so it's regular. So you cannot imagine a better coefficient. These are exactly the coefficients for which you can prove Schauder's theory. And then p is less than n, less than obviously n plus alpha, less than q. And then you get a solution to this Dirichlet boundary problem. It minimizes this one. U is Lipschitz. And you get a solution. The solution is obviously in W1Q, W1P, so the gradient is in LP trivially, because you are minimizing the energy, but the gradient fails to be in LQ. So this means you have a convex, a very regular convex scalar variational integral with a very good coefficient. That's a Hilder coefficient. Still, you don't get the basic bootstrap of regularity. Because, of course, for such kind of functionals, by the very definition of minimality and by the growth condition from below, coercivity, you always get a minimizer which is in W1P. What you actually cannot ensure, and what is actually failing sometimes, is that the gradient is in LQ. And eventually, in another paper with Fonseca and Mali, dating back 04, we proved that under the same condition, we can cook up another coefficient, and a minimizer, which is with set of essential discontinuity points. So the set where there is a discontinuity, the set of non-Lebesgue points, has Hausdorff dimension larger than n minus p plus something. Sorry, minus something for every epsilon. So you can so since a minimizer is in W1p by definition, the set of non-Lebesgue points has a Hausdorff dimension which is not exceeding n minus p. And now you can cook up a good coefficient and a minimizer whose bad set is almost, and a minimizer who is almost as bad as any other competitor. So this is telling you that no regularization effect whatsoever can occur under these conditions. And so this is that's the proof of the fact that when you consider non-autonomous functionals, and when you couple the presence of an external ingredient with the gradient, then the x is not a perturbation anymore, because essentially the very nature of the ellipticity of the functional is determined by the interaction between the x and the gradient. I'd like to consider there's a vast literature on both the functionals, especially on actually there's a vast literature on the first one. The second one is just starting. The second one is, in my opinion, much more interesting because it features a stronger transition between the two exponents. And it took a long while to understand how the regularity of this functional goes. And actually, it was very recent in a series of papers with Maria Colombo and Paolo Baroni. There are two papers by Colombo and myself on ARM 15, and then there are more recent papers with Baroni. And we were actually analyzing, and we came up with the following theorem that is clarifying the situation. So this is the theorem telling when things go wrong. And now let me tell you when things go well. And the final theorem is the following one. The theorem. So we take a minimizer, a local minimizer of this functional. Where a of x is assumed to be locally C0 alpha. Everything is local and blah, blah. So first, assume that Q is less than or equal 1 plus over n, then du is locally Hilbert. So there's no difference between the P Laplacian, the usual P Laplacian functional, and this functional. Observe that this is exactly the situation ruled out by the counterexample. So the bound is sharp, because otherwise you use the counterexample to see that the bound is sharp. Because you see, divide everything by p, and you see that this is failing. On the other hand, in the counterexample, you get a boundary datum which is W1 infinity. So this is a counterexample where by maximum principle the solution is bounded. The solution fails to be in LQ. Okay, the gradient of the solution fails to be in LQ. The solution is discontinuous, but the solution is bounded. And the difference between P and Q is larger than alpha. So we have a second theorem. If U belongs to L infinity and Q is less than or equal than P plus alpha, then du is locally Hilbert. And this actually, it's exactly the other situation that complements this. And finally, you know that when the regularity of U is growing, then the bound is better. So if U is now C0 gamma for some gamma between 0 and 1, and q is less than or is strictly less than p plus alpha over 1 minus gamma, then du is locally Hilbert. You see, when gamma is equal to 0, that is no Hilbert continuity, you get just bounded. So you get L infinity as the lower limit of Hilbert continuity, you get this bound. When gamma goes to 1, you are more and more requiring that the gradient is bounded up to the limit when there is no bound, because the gradient is already bounded. And then you can prove the rest. Two explanations, while there is this very subtle interaction between the variability with respect to x and the variability with the, and the gradient structure. Let's take this functional, and let me write down the Euler-Lagrange equation of this functional. If I write down the Euler-Lagrange equation of this functional, then I end up with the following equation. What's the ratio between the highest and the lowest eigenvalue? The ratio, the upper eigenvalue in a small ball, it's q minus 2, because that's the Laplacian and that's the eigenvalue a of x. The lowest one is due to the p minus 2. And this is this. Now you see, where is the bound coming from? Of course, I'm just considering the set where du is very large, because you have to prevent that du is blowing up under this situation. That's the counterexample. Now, on one hand, q minus p tends to blow up to make you lose uniform ellipticity. On the other hand, a of x helps you to get ellipticity. So if the sharp so if this is very small in a ball where the transition occurs, let's say a of x is 0, a of x is larger than 0. So the faster is the transition, the smallest is this guy. And therefore, you get exactly these kinds of bound. The interaction comes from this very fact. There's actually a deeper connection that can be exploited by using the following example. And that tells you that this is actually a capacitory condition. It's a capacitory condition. It's a capacitory condition. So let me take a ball centered at 0, and let me take some a of x which is disappearing as x to the alpha. What's the capacity associated to the p problems? The p capacity, the usual p capacity is given by capacity of a ball. P capacity is the inf of the energies P over Rn, and U is larger or equal than 1 on Br, and U is C infinity. Yeah. Okay. On the other hand, there is another term appearing in the functional, which is a term which is decaying as rho to the alpha. So the other capacity is the Q capacity weighted with something that is decreasing as xr to the alpha. So this is the typical capacity studied in Mazia papers and books. So that's Br, and that's applied by the inf. It's the inf of x to the alpha d to the q under the same conditions. Now, the capacity is really the object that regulates, in some sense, elliptic problems, because the removability of singularity is measured through capacity. It's some sort, it regulates the rigidity of the problem. Now, in the functional, you have two objects appearing. You have a priori two energies. This one and this one. A priori, this is the higher order energy. But let's see what is the contribution of this and of this in such a situation. The P capacity of a ball, it's well known to go as n minus P. and p is less than n. Let me consider the case p is less than n. Well, it's a simple computation that the other capacity, the qx, the q alpha capacity, let's say, the q alpha capacity goes like n minus q, but then you get alpha plus alpha. Right? So this helps to keep the energy low. This helps, it's a way that keeps the energy low. So a priori, you know that this is higher than this one, because you're minimizing a higher energy, but there's a weight that helps you. Now you want to prescribe the condition where the second term, which is a priori at the first sight the leading term, it's actually a perturbation of the first one. So you should prescribe that this capacity is controlled by the other one. So you want to prescribe that n minus p is less than or equal to n minus q plus alpha. And since r is small, this is the same that prescribing that this is n minus p, and this is, and what is this? This is essentially q less than p plus alpha. So this is a capacitary condition that tells you that the second term, although it looks as a higher order term, so in contributing the energy, then it's actually a perturbation of the first one. And this actually suggests the rate of the proof. The proof is done in a way here that the way we prove these theorems, which is natural but technically a bit involved. I mean, the proof, all in all, if you want to prove all these statements, it takes some long while. This is made on an observation. You take a ball, dr, and you argue on an alternative. There will be a universal constant such that if the inf over a of x is less than or equal of the ball, is less than or equal than this constant, the Hilbert continuity rho to the alpha, then you are exactly in this situation. And if, of course, one of these three bounds is happening, one of these three bounds is happening, of course, let me recall you that here, when you compute the capacity, u must be, let's say, equal to 1 and going to 0. So it's always bounded. If you prescribe that u is also Hilbert continuous, you come up with this. It's a capacitor issue. Okay, so you are in a situation where between the two energies, but just on this scale, this guy can be considered as a perturbation of the first one. This is completely unorthodox in the theory, because in the theory you look at the highest exponent involved in the gradient, and that should be the higher order term, right? The highest order term. Here you do the opposite, and so we treat this as a minimizer just of this. But minimizers of this are regular, and then you can go on with regularity. So in some sense, we do a scaling with the Hilbert continuity, and we look at that this can be absorbed, but just on that scale. For instance, if you get such a ball, it's not difficult to prove that things that are typically of homogeneous functions happen for this function. For instance, you can prove under this bound that they do satisfy a reverse inequality like this. This is a typical reverse inequality that certainly cannot hold at every scale, because this is a homogeneous inequality while the functional is not homogeneous. But when you prescribe that this condition is satisfied on that ball, then the reverse Hilbert inequality happens just on that ball, not at every ball. And this is the sign that the whole object behaves as this guy. So this is the leading term, and you are reabsorbing this. On the other hand, if this fails, well, if this fails, then a of x is large from 0 enough, and then you can prove that minimizers of this are similar to minimizers of this functional. Well, now this is fixed, constant. But minimizers of these functionals are regular, because now a is constant, and this is an all-H function. This is not a functional with PQ growth. This is functional with Q growth. So this becomes dominating, and you can absorb, in a sense, this in this. The combination of this alternative via some exit time argument. So you will start with a ball, and then you check if this is okay. Then I shrink and I check again. I check again up to the exit time where this is not satisfied. Then this is satisfied, but then the other one is satisfied at every scale. And then the combination of the two allows you to prove decay estimates for the gradient and eventually higher order regularity. So that's the main idea. But the main idea is that we take an unorthodox viewpoint, and the unorthodox viewpoint is that what it looks like an a priori higher order term can be turned into a lower order one and absorbed in this guy. Okay. Okay.